So last day we did the derivation of the different components of the short circuit current that flows in the circuit when a short circuit fault occurs. If we remember properly, then symmetrical short circuit fault is a fault which involves all the three phases of the line. There are two types of fault: symmetrical fault and unsymmetrical fault. The unsymmetrical fault involves one or two phases and not all the three phases. The most severe type of fault is the symmetrical short circuit fault, which involves all the three phases of the line. And the circuit breaker ratings are selected in such a way so that they are capable of withstanding or handling the huge amount of current that flows when a three-phase short circuit fault occurs. So today let us consider the sudden short circuit of a synchronous generator initially operating under open circuit conditions. The machine undergoes a transient in all the three phases, finally ending up in a steady state condition. We have learned in the previous class that there are three types, or rather three phases of this transient. There is the subtransient current, the transient current, and the steady state current. The total current comprises of two parts. One is the DC offset current and the other is the AC current. The DC current dies out uh, exponentially, as we have seen in the derivation in the final equation, whereas at the time of steady state, only the short circuit, rather only the three-phase current or sinusoidal current is there. The circuit breaker must interrupt the current much before it reaches the steady state value. Within the first few cycles, the circuit breaker must stop the current, otherwise uh, it can damage the different equipments that are present connected to the line. The DC offset current appears in all the three phases. Even though we are dealing with a single phase or a single line diagram, it means that all the three phases can be modeled by a single line diagram. So the DC offset current appears in all the three phases. For the short circuit studies, we need to concentrate on the symmetrical short circuit current only. Immediately after a short circuit, the symmetrical short circuit current is only limited by the leakage reactance. Since air gap uh, flux cannot change instantaneously, to counter the demagnetizing effect of the armature reaction, currents appear in the field and the damper windings in the direction of the main flux. That means as the flux cannot change instantaneously, and as the current has increased to a very high value, so the demagnetizing effect of the armature, or rather the part of the, or rather the demagnetizing effect of the armature reaction increases to a very high value due to the presence of a very high current. So uh, to counter this demagnetizing effect of the armature reaction, currents appear in both the field and the damper winding in the direction of the main flux. That is, it helps in keeping, or rather it aids the main flux, so that the amount of demagnetization done by the armature reaction is overcome and overcome by the flux created in the damper winding and the field winding, which is added to the main flux. That is, it is created in the direction of the main flux, whereas the magnetizing flux or demagnetizing flux created by the armature reaction is opposite to the main flux. So we can see that under steady state short circuit conditions, the armature reaction of a synchronous generator produces a demagnetizing flux. The effect is modeled as XA in the series with the induced EMF that we will see in the diagram. This reactance is combined with the leakage reactance XL of the machine, and this combination is called the synchronous reactance. That is, the leakage reactance of the machine which limits the flow of current during the fault. Now this thing to understand is that the armature reaction, or rather XA, is not an actual reactance. It is a modeling of the armature reaction or the demagnetization flux that is created by the armature reaction uh, in the circuit. It is the representation of the demagnetization flux in the circuit, and it is modeled as a reactance which is called XA, whereas XL is actually present, it is the actual leakage reactance which is present in the line and which limits the fault current which flows in the case of a symmetrical short circuit. Now this reactance, this XA combined with the leakage reactance XL of the machine is called synchronous reactance XD. During initial short circuit, the damper and field windings have transformer currents induced in them, as I have told earlier that during the initial short circuit, or rather just at the start of the short circuit, due to the demagnetizing effect of the armature reaction or the demagnetizing flux created by the armature reaction, the main flux is aided, or rather more flux is created in the damper and field windings to help the main flux keep its previous value. That is to compensate the main flux. The current is the flux is created in damper and field winding. Now how is the flux created? It cannot be created out of thin air. So it is created by the currents flowing in the damper and field winding, which has and how are the currents produced? They're induced in the damper and field windings by the reactance, or rather by the flux. So this is our circuit diagram, which is in the subtransient phase. We have the voltage source, which is modeled as EG, and there is a little bit confusion with XL. Here we can see XL. This is XL, leakage reactance. This is XA, the demagnetizing effect or demagnetizing flux created by the armature reaction, and this is XF, that is the flux that is created in the field winding in the direction of the main flux to compensate the main flux, and XDW, that is the flux or rather damper winding reactance, which is also or rather this flux in this damper winding is also aiding the main flux. So we have got XL, which is limiting the short circuit current that is flowing in case of a fault. Here we have a switch. If we close the switch, it will represent a short circuit symmetrical fault, which involves all the three phases. This is a single line diagram which represents all the three phases, and we know that the conditions, as is a symmetrical fault, the conditions are similar in all the three phases. So if I study only one phase, I can safely say that all the other two phases are going through the same reaction, just limited by the presence or the limited by the uh, limited by the position of the voltage wave at the point of fault, because the three phases have different voltages and not different voltages. Their voltages are phase shifted by an angle, as we know. So at a certain point, if a fault occurs, then the voltage waveforms will be at different positions in the time axis at that particular point. So that is the only thing that is different in the three phases, but otherwise all the three phases act as the same. That means if this phase has XL, XA, XF, XDW, all the other two phases also have these. So XL is the leakage reactance, XA is the demagnetizing reactance, or the reactance which models which is modeled for the demagnetizing effect of the armature reaction, and XF is a field reactance which is present due to the currents induced in the field, and XDW is the damper winding reactance which is also present due to the current induced in the damper winding. Both these flux aid the main flux. Now initially the reactance of the machine is called the subtransient reactance. So we have the subtransient reactance formula here, that is XD dash dash. We can see XL is in series with the parallel combination of these three reactances. So XL plus 1 by XA plus 1 by XF plus 1 by XDW. This is the parallel combination or the resultant of the parallel combination of these three reactances, and XL is in series, so we directly add XL to the parallel combination of the three reactances. This is the direct axis transient reactance. So during the transient phase, what happens? The current in the damper winding dies down, that is XDW, that is the previous slide. We have XDW. During the transient phase, when we move from the subtransient to the transient phase, the XDW becomes open circuited as the damper winding currents die out fast as the uh, damper windings at the lowest time constant. So the damper winding currents die out fast. Then the XF becomes open circuited. So after damper winding, XF will the current in the field windings will die out, and then during the steady state only XL and XA will be there. So in the subtransient state we have all of these three reactances. Then we have removed XDW. The currents in the damper windings have died down as the time constant is minimum for the damper windings. Then we have the transient reactance, which is XD dash, which is equal to XL plus the parallel combination of XF and XA. So XD dash is equal to XL plus the parallel combination of XA and XF. Then we have got the synchronous reactance, that is the steady state reactance. We know that after XDW, XF becomes open circuited, that is the current in the field windings die down. Finally, we reach the steady state reactance, which is not supposed to be reached if the circuit breakers activate properly. And it is an easy combination. We can see that XD is equal to the series combination of XL and XA. So XD is equal to XL plus XA. Obviously, we can understand that XD dash dash is less than XD dash, and which is less than XD. So subtransient reactance is the lowest. Transient reactance is higher than subtransient reactance but lower than steady state reactance, and steady state reactance is the highest. So from the currents and reactances, we can say that the steady state current is equal to EG, that is the voltage source voltage value, by XD. The transient current is equal to EG by XD dash, which is the transient reactance, and the subtransient current is equal to EG by XD dash dash, which is the subtransient reactance. Now for symmetrical fault calculations, what we have to calculate in case of a symmetrical fault, or how are the calculations important? So you can see that the rated MVA breaking capacity of the circuit breakers are based on three-phase fault MVA. As we know that the three-phase faults are the most severe faults that can occur in a power system. So the circuit breakers should be able to handle the fault currents and MVA of the three-phase fault. So the circuit breakers are selected in such a way such that their rated MVA breaking capacity is based on the three-phase fault MVA. Generally for three-phase fault calculations, following assumptions are made. This we'll see while we'll be doing the problems. The EMF of all the generators are taken as 1 angle 0 per unit. This assumption simplifies the problem, and it means that the voltage is set to nominal value and the system is operating at no load at the time of fault. Since all EMFs are equal and in phase, all generators can be replaced by a single generator. Charging capacitances of the transmission line are neglected. Shunt elements in the transformer models are neglected. So any shunt elements and capacitances of the transmission line and transformer models, they are neglected, and this is simply done to for the ease of calculations, as the difference created by this charging capacitance and shunt elements is not very much in case of a short circuit fault. So we have a problem here. We can see the problem. A synchronous generator and a synchronous motor, each rated 20 MVA, 12.66 kV, having 15% subtransient reactance, are connected to transformers and a line as shown in the figure. So here we have got a synchronous generator and a synchronous motor. Each are rated as 20 MVA and 12.66 kV, and they have 15% subtransient reactance. The transformers T1 and T2 are rated as 20 MVA, 12.66 to 66 kV. So this is a step up transformer which is stepping up from 12.66 kV to 66 kV, and this is a step down transformer which is stepping down from 66 kV to 12.66 kV, with leakage reactance of 10% each. The line has a reactance of 8% on a base of 20 MVA 66 kV. So this is our base for the line, 20 MVA 66 kV. The motor is drawing 10 megawatt at 0.80 leading power factor and a terminal voltage of 11 kV when a symmetrical three-phase short fault occurs at the motor terminal. So the fault is occurring here at the motor terminal. Determine the generator and the motor currents, and we have also have to determine the fault current. So we can see that all reactances are given on a base of 20 MVA and appropriate voltages. So from the previous slide we can see that 20 MVA here, we have got 20 MVA. The motor is also 20 MVA. The transformer is also rated at 20 MVA. And this is the percentage reactances which are given on these base MVAs and the appropriate voltages. So we do not have to take another voltage. So pre-fault voltage is V0, that is before the fault occurs. What is the voltage? V0, that is 11. We know that it was 11 kV at the terminal of the motor. It was 11 kV, and our base voltage is 12.66 that we have obtained from this point. So on the low voltage side of the transformer, the voltage is 12.66 kV. So our base voltage is 12.66 kV. So 11 angle 0, 12.66 divided by 12.66, that will give us 0.8688 angle 0 in per unit. We know the load is 10 megawatt and the power factor is 0.80 leading, which is equal to, if we convert it into per unit, we have the base of 20 MVA. So 10 by 20, that is 0.50 per unit. And so we can get the pre-fault current, which is equal to 50 by 0.8688 into 0.80 angle 36.87 degree, which is equal to 0.7194 angle 36.87 degree. Sorry, this will not be equal to 50, this will be equal to 0.50, this one, megawatt. So 0.50, we have a leading power factor 0.80, which gives us the angle 36.87 degree, and 0.8688 is the terminal voltage at the motor, and this is the 0.80 power factor. So this is a pre-fault equivalent circuit. We had the reactances at 15% for both of this. So per unit reactance is 0.15 and 0.15. For transformers we had 10%. The per unit reactance is 0.10 and 0.10. So the equivalent circuit during fault will look like this. Our fault is at the motor terminal. So this is the fault line. Current is flowing both from the motor terminal and from the generator terminal. We have added this up, so this goes up to J 0.28. So 0.15, 0.28, and the current is flowing through these two reactances. And here the motor current IM dash dash is flowing through this 0.15 J 0.15 reactance. This is a bit hazy, but I think it is understandable. So from the pre-fault equivalent circuit, voltage behind subtransient reactance generator is EG is equal to V0, which is the pre-fault voltage, plus J, the whole of the reactances present, multiplied by I0, which gives us EG dash dash is equal to 0.7266 angle of 19.9 degree per unit. Similarly, EM dash can be obtained to uh, to get the value 0.9374 angle minus 5.28 degree per unit. From the equivalent circuit during fault, we can get Ig dash, which we know at Eg dash dash Ig dash dash is equal to Eg dash dash by Xd dash dash. So you get the value Ig dash dash, and then we convert it to the rectangular form. This is the polar form, we convert it to the rectangular form. Similarly, we get Im dash and we convert it to the rectangular form. The total fault current in the previous diagram, as we have seen, that If was equal to Ig dash dash plus Im dash dash. So we add and we get the fault current. Now what is the base current for generator motor? That is Ib is equal to 20 MV, so 20 into 10 to the power 3 by root 3 into 12.66, which is the base voltage at both the generator and the motor end. So this is our base current. When we multiply the per unit currents with the base currents, then we will get the actual value of the current. So we multiply the per unit value of these currents with the base current to get the actual value of these currents. So Ig dash dash is equal to 1540.5 angle minus 70.1 ampere. Im dash dash is equal to 5700.5 minus 95.28 degree ampere, and If is equal to 7124.3 angle of minus 90 degree ampere. So next we go on to the rated MVA interrupting capacity of a circuit breaker. The circuit breaker rating requires the computation of rated momentary current and the rated symmetrical interrupting current. We have found out that the rated momentary current, which is a combination of the DC offset current and the sinusoidal current, which appears at the start, which can reach almost twice that of the current value, and rated symmetrical interrupting current is also needed for the circuit breaker rating. Computation of symmetrical short circuit current requires subtransient reactance for the synchronous machine that we have already seen. We require the subtransient reactances for the synchronous machines to get Ig dash dash. RMS value of the momentary current is then computed by multiplying the symmetrical momentary current by a factor of 1.60 to consider the effect of DC offset current. So that means that the momentary current is not separately calculated. We calculate the symmetrical short circuit current by using the subtransient reactances of the synchronous machine, and that value is multiplied by 1.60 to take into effect the DC offset current, to consider the effect of DC offset current. So DC offset current is not separately calculated, simply the symmetrical short circuit current is multiplied by a factor of 1.60. The interrupting current of a circuit breaker is inversely proportional to the operating voltage over a certain range. That is, IOV is equal to IR into VR by VOV. Where IOV is the current at operating voltage, so OV is operating voltage, IR is the current at rated voltage, VR is the rated voltage, and VOV is the operating voltage. The operating voltage cannot exceed the maximum design value, and the rated interrupting current cannot exceed the rated maximum interrupting current. So previously we have a design value for the operating voltage and the rated maximum interrupting current. So for a particular circuit breaker, if we have to use that circuit breaker into a particular line, we have to take the precautions so that the operating voltage during the fault cannot exceed the maximum design value, and the rated interrupting current, that is the current it will have to break in case of a fault, cannot exceed the rated maximum interrupting current which is specified for the particular circuit breaker. So the three-phase rated interrupting MVA capacity of a circuit breaker is given as MVA rated three-phase, which is equal to root 3 multiplied by V line R, that is rated line voltage, and I line RIC, that is rated interrupting current in kiloampere. Both the voltage and the line and the current are in kilo units. That is, voltage is for kilovolt and I is kiloampere. Here you can see that V line R is rated line voltage and I line RIC is rated interrupting current for the line kiloampere. So the three-phase short circuit MVA to be interrupted where is short circuit MVA three phase, that is equal to root 3 of E0 multiplied by ISC into MVA base, where E0 is the pre-fault voltage which we have found out in the previous problem. We have seen that we have to find out pre-fault voltage. ISC is the short circuit current in kiloampere. MVA rated three phase is to be more than or equal to the short circuit MVA required to be interrupted. This goes as per the instructions given that was mentioned in the previous slide, that the operating voltage cannot, or rather the operating voltage cannot exceed the maximum design voltage. Similarly, the power, that is MVA rated three phase for the circuit breaker has to be more than or equal to the short circuit MVA. The short circuit MVA that is present in case of a three-phase symmetrical fault in the line where the circuit breaker is installed. So the MVA, three-phase rated MVA of the circuit breaker has to be more than or equal to the short circuit MVA of three-phase fault required, that is required to be interrupted. A three-phase short circuit is very rare, but it gives the highest short circuit MVA, and a circuit breaker must be capable of interrupting it. So we have already learned that a three-phase short circuit is very rare, and it generates the highest amount of current in the line. So the highest short circuit MVA gives the highest short circuit MVA. It also gives the highest short circuit MVA, and the circuit breaker must be capable of interrupting a three-phase symmetrical short circuit fault. So if a circuit breaker is capable of interrupting the three-phase symmetrical short circuit fault of a line, it is considered to be capable of interrupting the unsymmetrical faults, which gives rise to much lesser currents compared to a three-phase symmetrical fault. Next we come to current limiting reactors. The short circuit current is large enough to do considerable damage mechanically and thermally. That is clearly understandable. The interrupting capacities of the circuit breakers to handle such currents have to be very large to reduce this high fault current, and to make it possible to use the circuit breakers of lower ratings, we can connect artificial reactances between bus sections to reduce the fault current. And obviously if we reduce the fault current, we can reduce the ratings of the circuit breakers connected in that line. These current limiting reactors usually consist of insulated copper strip embedded in concrete formers. This is necessary to withstand the high mechanical forces, that is, the mechanical support given by the concrete formers is necessary to withstand the high mechanical forces produced by the current in the neighboring conductors. So now let us go to some problems. Please follow the next video for these problems, explanation of these problems.